You have to study the session number 10, 11 and 12, and some part of the 7 for diaphragm from the medical embryology of the lineman. Okay, lineman's medical embryology. I know you have this book. If you don't, I can send the PDF file for Ahmed, and he can forward for all the students. Okay. I didn't hear. Did you? Somebody talk to me, I think. Do you hear me? Okay. The skeletal system developed from the paraxial mesoderm, lateral plate mesoderm, and neural crest. You know, we have a three part in a mesoderm. Here is the ectoderm. Yes, you can see here is a neural tube, a neural groove, and after that the neural tube. Here is the red part is mesenchyme layer, and here is the endodermal. Here is the ectoderm, and you know the mesenchyme have a three part. Some part is near to the axis. The axis is notochord. We say the paraxial mesoderm. The paraxial mesoderm in a head region is a somitomer, and in occipital and cervical, and after that until the tail body is somit or somites. The next part of the mesoderm, sorry, the mesenchyme is that's mesoderm, the mesoderm, paraxial mesoderm. The next part is intermediate, that your genital develop from the intermediate mesoderm. And the next part is lateral plate mesoderm. You know, the lateral plate mesoderm is split into two layers. One layer covered the yolk sac. This part is the yolk sac, and make a splanking mesoderm. We say splanking or visceral mesoderm, and the parietal layer is under the Farah. Please wait. Okay. The parietal mesoderm, that's the part is under the ectoderm and cover the inside of the ectoderm. And you know, the skeletal mesoderm differentiate from some part from the paraxial mesoderm, some part from the lateral plate mesoderm. And in the face and skull, the neural crests have an important role in the bones of the face and skull. Okay, they spread in that bones and make a special bones for the skull and face. But some part of skull built by or formed by the somite or somitomer. That's the paraxial mesoderm. So we have a three source for skeletal system. The first is the paraxial. Here is the paraxial. The paraxial make make a vertebra. Okay. The second part is lateral plate mesoderm. This is a lateral plate mesoderm, what means the parietal layer of lateral plate mesoderm make bones for the pelvic and shoulder girdle, limb, and the sternum. Wait a minute, I'm coming back to class. And the third source for the skeletal system of the face and skull is neural crest. You can see here between the border between the somite or somitomer or paraxial mesoderm and the lateral plate mesoderm is just a green line. This line is a lateral somitic frontier, means the border between the lateral plate mesoderm and somite. Okay, we say the lateral somitic frontier. Some cells from the paraxial mesoderm can immigrate to the lateral plate mesoderm and make a bone. Okay, every somite have it's like a ball shape. You can see that's at the first of the differentiation, it's like a ball with a hollow in the middle, and here that's the ventral surface, and this part is a dorsal surface. In a ventral, this part is a sclerotum. Okay, the sclerotum is differentiated to the bones, to the vertebra. Some part of the skeletal immigrate around the notochord and the neural tube and join with the opposite other side and make a block around it, and that block differentiate to vertebra. Some of the cells of skeleton stay here and then start to growing and goes to the lateral plate mesoderm and make ribs, but the bone part of the rib. And some part of the skeleton immigrate to the lateral plate mesoderm and make a costal cartilage. Okay, so I repeat again. Any somite or somitomer at first of differentiation convert to the ball shape. Okay, that's epithelialization occurring in a mesoderm. The ventral part is a skeleton, and the dorsal part is a dermatom myotom. Dermatom means make it dermatom, and myotom is for the muscle, means the origin of the muscle. The skeleton that means that the ventral part at first convert to the mesenchyme. What's the mesenchyme? Means that the embryonic tissue. This cell is a connected tissue of the embryo. That's this cells. The character of these cells is different with the that's a the skeleton cell become polymorphous and a loosey tissue here, and we say the mesenchyme. So the skeleton convert to the mesenchyme. Some of cell go around the axis, means the neural tube and notochord, and make a vertebra. Some of the cells stay here and don't immigrate to the lateral plate and make a bone part of the ribs. And some of the skeleton cell immigrate to the lateral plate mesoderm, pass away the disc border, the lateral semitic frontier, and make a costal cartilage. Okay, and the cell in the lateral, the lateral plate mesoderm from skeletal make a pelvic, shoulder, and pelvic and shoulder girder, limbs, bones like a humerus, femur, and also the sternum. Okay, these cells, the origin of these cells is come from the lateral plate mesoderm. They are these cells. This part, the lateral plate mesoderm, is not come from the sclerotum. The sclerotum is just for the vertebra and rib. Got it? But the lateral plate mesoderm means this part. The cell here convert to the pelvic, shoulder girder, limbs, and the sternum. And the third source of the skeletal system is neural tube, neural crest. The neural crest is for bone of the skull. Okay. You can see here how the sclerotum, this cells, convert to the vertebra. As I told you, at first the sclerotum cells convert to the mesenchyme, means it become polymorphous and a loose organized tissue. When the cells go around the axis, means notochord and neural tube, make a block around it like this. Okay. For example, this is from one somite. The somite is a block shape, and we have, for example, 8 block shape in a cervical part, 4 in the occipital, 12 in the thoracic part, and in a lumbar part we have 5 in the sacral part we have 5 somite. And every of this somite, the sclerotum of them make a one block around the notochord and also neural tube. With the immigration and making a block around the axis, we have this shape. Okay, this shape is and they convert to the bone. And the bones, means a vertebra. But if you look here, in a dorsal part of the sclerotum, we have a dermatomyotome. What is the dermatomyotome? The middle part is dermatome. Dermatome is a part of the skin, okay? The deep part of the skin after the epidermis, derm. In anatomy, we say the superficial fascia. Okay, so the dermatome means a part of a skin that innervated by one spinal nerve. That's the definition of the dermatome. A part of the skin that innervated by a spinal nerve. But you can see in a dorsomedial part of the dermatome and ventromedial part, we have a myotome. And this myotome converts to the progenitor cells of the muscle, and we say the myoblast. And after that, the myoblast differentiate to myocyte, and the myocyte fuse together and make a muscle. Okay, the dorsomedial part of the myotome go around again around the disc block and differentiate to the muscle. At first, you can see the sclerotome differentiate to the bone, and dorsomedial part of the myotome convert to the muscle. You can see the nerve here that exit from the middle of the disc block, and the artery exit from the inferior part of this segment or the block. But if the muscle work, the vertebra don't move. Why? Because the origin and insertion of the muscle attached to the one block. After this step, we have a resegmentation. This part is a segmentation because it is every sclerotome from the somite is a segment by segment. Okay, every of the sclerotome make a segment, and this segment in the next step we have another process. That process is a resegmentation. Means because this segment have a special character. Look here. For example, this is a segment from the sclerotome. Have a three part. The cephalic part. Here you can see a line here. We say the von Ebner and the caudal part. The characterization of the cell in a caudal and cephalic part is different. The proliferation in a cephalic part is low, but the proliferation, the cell proliferation of the distal part of the segment is rapid. And von Ebner haven't any proliferation. It's mean the cell when the cell here start the proliferation that fuse to the cephalic part of the next segment. Okay, this part join together and fuse together and make a new segment. Okay, so every vertebra have a two part here. This part from the caudal part of the primary segment, and this part is a cranial part of the next segment. As I told you, between them at the first segment we haven't any proliferation, and it make it intervertebral disc. Okay, but what happened for the notochord? The notochord disappear in a vertebra, but just leaves a part inside the intervertebral disc, and it make a the core of the disc, you know, that every disc have a two part. The circular part, the lateral part is annulus fibrosus, but in the middle, that's like a gel, and that's a nucleus pulposus. So the notochord in an adult is make an interstitial, that's an intervertebral disc. We come back to the before slide. So we review again. The sclerotom immigrate around the axis, make a segment, and the myotome differentiate to the muscle on that segment. The nerve exit from the middle of the segment, and the vertebra from the inferior part of the segment. The character of this segment is different between the different part of it. In a cranial part, the proliferation is low, and in a caudal part, the cell proliferation is rapid, and in the middle we haven't any proliferation. It causes the fuse, the distal part or the caudal part of the segment fuse to the cranial part of the next segment. And we say this process resegmentation, and you can see the resegmentation here. With the resegmentation, we have a vertebra, and you can see the alternation of the or change the citation, the site of the muscle, because here the muscle bridge between the two vertebra, and now it can move the vertebra. And here you can see they change the site of the nerve and vertebra. They both exit from the middle of the vertebra, because here the artery is from the inferior part of the segment, and the next, after the resegmentation, it exits from the middle. And finally, you can see the nerve exits from the inferior. But in adult, the artery and the nerve exit from the disc canal. You know, that's between the vertebra. We say intervertebral foramen. Okay, that exits from this area. Okay, that's for example, this shape show you for example, this C1, C2. The C1 was made by the C1 and the C2. Okay, the caudal part of C1 and cranial part of the C2. Again, C2 from the caudal part of C2 and cranial part of the C3. And the middle of them, you can see the intervertebral and notochord disappear in the between the vertebra, just lives in an intervertebral disc here. And finally, the notochord differentiate to nucleus pulposus, the core of the disc, and that's a jelly shape. Okay, but come back here. But the development of the limb, what happened when and how the limb is formed? You know, the 3 week of the gestation is the gastrulation. Start with the gastrulation. Okay. The 3rd week until 8th week is the embryonic period, and in this period we have a miniature human, and after that all organ start to the maturation. About the fourth week, most of the organs start to the formation. For example, the limb, the respiratory system, the liver, the gut, all of them start to the formation. The limb starts with the limb bud, with the bud in a lateral plate mesoderm. Okay, the lateral plate mesoderm outgrows to the lateral of the body, and here covered by the ectoderm. Okay, so this part is the parietal or somatic layer of the lateral plate mesoderm that covered by the ectoderm. The ectoderm make a skin, and somatic layer of the lateral plate mesoderm make bones and massa. This bud have that's a starting in the outgrowing of the limb bud start with in a fourth week. The characterization of this bud, if you look here, is different in the apical, in the distal part here, in the tip of the limb here. The cells are different with the other part, and we say the apical ectodermal ridge. The apical ectodermal ridge, the cells here have a special characterization. The cell here exert an inductive influence on the underneath mesenchyme. What is the inductor? That's an inducer here, okay? That's a make a induction effect or influence under the mesenchyme here. What is the induction? The induction it's mean it's cause the cell near to the apical ectodermal ridge stay undifferentiated. Means the apical ectodermal ridge prevent the differentiation of the cell near here. But the cells that farther, that's far from the apical ectodermal ridge, start the differentiation. Differentiation means differentiate to the bone, the connective tissue to the muscle. Okay, but the cell, the near here, start to the proliferation, rapid proliferation without any differentiation. In this manner, the development of each limb start from the proximal to the distal, because we haven't enough induction here, and it start to the differentiation, and it differentiate to the three part: stylopod, zygopod, and autopod. Stylopod make a humerus and femur. Zygopod, the part is the forearm, okay, the bones of the radius ulna, and in a lower limb is tibia and fibula. And autopod is a hand, okay, the carpal bones and metacarpal and digits, and tarsal bone in the lower limb, tarsal, metatarsal, and digits bone. As I told you, the limb growth and development start in the fourth week. At the fourth week, you can just see some part one to the outcrossing and make a limb bud here. At the 5 week, the 5th week, we have a 2 limb bud without any changes in the morphology of the limb bud. But in a 6th week, we have a changing in morphology, change of morphology of the limb. But here you can see the distal part of the limb start to the become flattened and form a hand and make a hand plate. There's a hand plate, and in a foot, we say the foot plate. And it's separate with the proximal part with a constriction here, and the constriction make the upper limb to the 2 part, the proximal and distal. And in next step, the proximal part again appear another constriction and make a 3 part in the upper limb and also in the lower limb. For example, here arm, forearm, and hand here. So in a 6th week old embryo, as I told you, we have a foot plate and hand plate. At the same time, the first model of the cartilage appears in a limb bud, but I discuss about that in the next slide. But you can see it's in a 6th week, we have a foot plate and hand plate. But what happened for the foot plate and hand plate? As I told you, the apical ectodermal ridge is in a distal part of the limb bud, okay, here. You can see the blue part is a cartilage, okay? That's appear in a 6th week. But you know we have a 5 finger. If you look the red part, in this area we have a apoptosis or the cell death. The cell death means the apical ectodermal ridge divide to the 5 part, okay? 1, 2, 3, 4, and 5. And in this area, we have a apical ectodermal ridge again. And it means it have a induction under the mesenchyme, means it's growth. And after that, we have a 5 finger. And they grows and make a 5 finger. And the tissue between the finger disappear because of the cell death. So in a 4th week, start of the limb bud. In a 5th week, we have a limb bud that's like can anybody Persian paru? What's the meaning of paru? Paddle, like paddle in a boat. It's like that. And in a 6th week, we have a foot and hand plate, and after that we have a cell death between the foot plate and hand plate, and every part means the apical ectodermal ridge divided the 5 fingers, and the outgrowth of the apical ectodermal ridge make a fingers. But what happened in a 7th week? In the seventh week, we have a rotation in a upper limb and lower limb. You know, the upper limb and the lower limb the development of the both limb are similar, but the morphogenesis of the lower limb is about 1 or 2 days behind that the upper limb. Means at first the first upper limb appear, and after 1 or 2 days continue the lower limb development. For example, the upper limb bud appear in at the first begin 28, but in a lower limb appear in a 30 days. Sorry, with a 1 or 2 day difference is between the upper and the morphogenesis of upper and lower. Okay. But in a seventh week, we have a rotation in the upper and lower limb. In the upper limb rotate in opposite direction, upper limb and lower limb. The upper limb rotate 90 laterally, means it's like a anatomical position, okay? In anatomical position, we say the palmar surface look forward, okay? And the thumb is in lateral, and the little finger is in the medial. When we have a lateral rotation we have a lateral rotation in an upper limb, and medial rotation is about 90 in a lower limb. When we have a lateral rotation, the pollex or thumb lie in a lateral, and little finger lie in a medial. Opposite, vice versa, in a lower limb, the big toe is in the medial, and the little finger is in a lateral. Notice too that in the upper limb with this rotation, the flexor compartments, the flexor muscle is in anterior compartment. For example, in arm, the biceps in anterior, and the extensors muscles in a posterior, from the triceps in a posterior, and extensor of forearm in a posterior. But in the lower limb, extensor is in a lateral, in an anterior. For example, the quadriceps and the extensor muscle of the hallucis longus and digitorum longus, all of them is the anterior, and in the posterior compartment we have a flexor. Upper for medial, lower. No. Muhammad Mohsen Said, no. Upper limb in lateral, rotate to lateral, and the lower limb rotate to medial. Or medially, yes. So, in a fourth week, we have a limb bud. In a fifth week, we have a limb bud. In a sixth week, we have a foot plate and a hand plate, and start the cartilage modeling. Start the forming of the cartilage. And in a seventh week, we have a rotation, and start to differentiation of muscles. That's important. put all the important event during from the 4th until the 7th. 4th and 5 limb bud. 6 we have a hand plate and foot plate, and also making the cartilage. 7th we have a rotation laterally in an upper limb, medially in a lower limb, about 90 degree, and also differentiation of muscle in a 7th week. This is a scanning electronic microscope. You can see the in a about between the 6 and 7 about. You can see this part is for this cell death, and the apical ectodermal ridge start to the grossing and make fingers. That's the fingers finally is like this. It's about is 56 days. Means about near 8 week. Okay. That's a film I'm trying to wait a minute. Oh, where is the film? Okay. This film have a two part. At first, show you the appearance of the upper limb. The upper limb, the side of the upper limb, detect by the expression of gene expression. You can see the upper limb bud, and the tip of the limb bud is the apical ectodermal ridge, and when it start growing, just so next 1 or 2 days appear the lower limb bud, and with have a delay ratio to the upper. Here is a hand plate, and you can see the digital or fingers. Here is a notch between the digital rays, and cell this between them, and the finger growing and make a thumb in anterior and little finger in a posterior. But after that, we have a rotation, but that's not right. That's not right here. But in the lower limb is correct. We have a medially rotation 90 degree in a 7th week. Here you can see the rotation from the anterior. In a 7 week, you can see the upper limb, and it's bigger than the lower limb bud. It's started growing. After that, in a 6 week, we have a hand plate, and start to appear the fingers, and it's in anatomical position of in the embryo. But the rotation in upper limb is not correct, but it's here because it have to rotate to the laterally. But the rotation have a effect on the dermatome. The dermatome is a part of the skin innervated by the one nerve. Wait a minute again. Look here. Okay, look here. You can see the upper limb bud is against the dermatome of the C5, 6, 7, 8, T1, and T2. And you know, this segment, that's nerve that innervated this dermatome, make a brachial plexus. Okay, at first that's a regular, and that the organization is so regular, and after that, after the rotation, it changed. Look here, that's for the lower limb is opposite the L3, or sorry, L2 until the S3. Look here, for the lower limb, for the upper limb, and that's outgrowing in a 6th week, the plate and hand plate, and in a 7th week, we have a rotation. When the rotation, they make different and change the site of the, look here, look there. All of the dermatome change with the rotation. Okay. Ali Abu Abbas, yes, 90 degree. But how to cartilage, how the cartilage is formed? The cartilage, that's differentiate from the mesenchyme. That's mesenchyme come from the myotome, from the sclerotome. The mesenchyme can differentiate to bone, cartilage, connective tissue. At first, for the, we have a two model of the bone formation: endochondral bone formation and intramembranous intramembrane bone formation. In endochondral bone formation, at first we have a cartilage model, and after that it remove and substitute by bones. But in a membranous bone, in an intermembranous bone, the mesenchymal cell directly differentiate to the bone. For example, in a skull, parietal bones, for example, directly differentiated to the bones. But in a humerus, femur, and the long bones, all long bones, at first we have a model, cartilage model, and after that, the ossification, the primary ossification center appear and remove the cartilage, and the bone substitute to the cartilage. The clavicle, all part of the clavicle is it's a membrane, intramembrane bone, but the middle part, and the acromial end, is a intrachondral, and ossification center appear in a 20 years old and complete in a 25 years old. As I told you, that's the best age for the marriage, but it's the idea of the Singh. The Singh is the author of the anatomy in India. Okay. But how to that's a cartilage. The cartilage appear in a fifth week. Let's show you the uh, intercondylar, and here show you the formation of the joint. You know, we have a joint between the bones, and in this area we can move bones ratio together. Okay, the site of the the joint, we say the intrazone area. Intrazone area. That's a in, induction by a gene that show the positioning of the for example, here is between the two cartilage. We want to make a joint. So in an intrazone, and the joint intrazone induced by a gene. That's a VENT14 is a gene that induced the positioning of the joint. At first, in the intrazone, the number and the condensation of the cell increase, and after that, the cell disc make a cavity here, and that cavity is a joint cavity. And you can see some part of this ossificate, this intrazone, because as I told you, this cells is a mesenchyme, and this mesenchyme can to differentiate to the chondrocyte and make a articular cartilage, or make a ligament. For example, here is a menisc and disc and joint ligament. But the joint capsule, the joint capsule is different. The origin of the joint capsule is different which other part of the capsule. The joint capsule is derived from the mesenchymal cells around the intrazone. Okay, this part is this capsule. The cells around it make a capsule, but the ligament, the menisc, disc, and all and the cavity and all part inside the capsule, inside the joint, derive from the intrazone, from the cell that's in intrazone. Okay, got it? Got it? Okay. For example, you imagine elbow. Elbow is between the arm and forearm, and the location of the at first for example, here's the arm and here's the forearm. For example, here's a humerus and here's the ulna, and it want to be make a area. We say that the intrazone convert to the cavity and make a joint. At first, here's a model, here's a cartilage model, and here's a cartilage model. Between them is intrazone, and this at first the mesenchyme is derived from the skeleton, and it's the cells without any special shape. That's polymorphous and loosey tissue. Okay, that can convert to the or differentiate to the cartilage and differentiate to ligament, connective tissue, and all parts like this. In intrazone, the number and the condensation of the cell increase. After the rising of the condensation, cell death starting. Is started. Sorry. Cell death started. And you can see some cavity here, and after that they connect to each other and make a cavity. That's a joint cavity. Some remind, or some part of the that lives from the cell death is a ligament. It's differentiate, or not? It's not differentiate. That's a part of the ligament joint, part of the meniscus and disc. All of them different is lives from the cell death in an intrazone. But the joint, the joint capsule is different, because some the cell, mesenchymal cell around it, can differentiate to this joint capsule. But the ligament, meniscus, disc, that's this part formed from the intrazone regions. Got it? It was enough. Okay. What about the muscles? As I told you, a sclerotum, that's a sclerotum, have a two parts, ventral part, dorsal part. Ventral, we say, or known as sclerotum. The sclerotum make a vertebra, make ribs, make means the ribs, just the bones part, and the in a dorsal part we have a three part. In the middle we have a dermatome. In a medially and laterally of the dermatome we have a the sternum directly differentiates from the lateral plate mesoderm. Sternum is a bone between the rib in the anterior part of the heart. Okay, in the middle of the thorax, that's a sternum. What happened for the myotome? Here is a dorsomedial, here is a myotome, and here's a ventrolateral, because it's a ventrolateral. Here's a dorsomedial. The dorsomedial differentiate to the muscle around the vertebra. Okay. But what happened for the ventrolateral muscle? Some of muscle that lives here, and some of them migrate to the lateral plate mesoderm. Okay, wait a minute.